Okay, so let's continue. We're going to focus on those 10 containers, which are 10 nodes that are running. And then what's important is this MRMS is the container that's going to show you the mapping system. And we can look at the mapping system through this web interface here. And we'll get through that in a moment. So what we're going to show you is we'll go into one of the containers, show you around. We'll show you what all 10 of them are doing to the mapping system. They're all registering to the mapping system. And then we'll show some multicast. We'll show that how everybody is joined to this group 224.111. And containers 2, 4, and 6 are joined to this group, and containers 3, 5, and 7 are joined to that group. And we'll show you how all that works. And basically what we're doing, so the Nexus is running, it's not doing anything interesting, but just keeping up the TCP connections. But I'll run some mesh pings to show you that we can send packets to all 10 and also multicast ping. Okay, does that seem pretty clear? Okay, so when I do this, this is showing you the 10 containers that are running. Now they've been up for quite a long time. We started this demo many months ago in anticipation for the Nexus Conference, and I didn't want to take them down. The 2 crypto ones that we'll show in the next meetup, I took down and brought back up to do some testing, so we'll show that next time. Okay, so if we look at XTR1, this is kind of interesting, is you see that these pings are going. This ping mesh that I started went indefinitely, and I started it on the stage at the Nexus Conference, so it keeps running. What it's trying to show you is, so this guy's EID is 1.1, you see it there in the middle of the screen, and he's basically pinging 2.2, 3.3, and 4.4. So let's let that go, and let me show you what the topology actually looks like. Okay, so if you look at this top screen here, we're showing that we have these XTRs. You know, we were playing around with the number of different ones. We only have 10 right now, not 100. But they're actually attached to this underlay. And this underlay is actually addressed. Treat this as the capital I internet, where these are your Nexus nodes, your wallets. They can be anywhere in the internet. And then the underlay actually moves packets from RLOC to RLOC. What we want to show is that the map server is reachable through this one address, in other words, 1.0.0.1, and that each of these XTRs are multi-home. That means they have an interface to the one network and to the 172 network. So you would see 1002 would be XTR1 and so forth and so on, okay? So let's just first look at it from a global point of view. This is the map server, looking at the container. I just refreshed it. And you can see all 10 of them are registered. Okay, what are they registered with? Well, their EIDs are registered in a specific instance ID. The instance ID is like a closed user group or VPN. And we can use this in many different ways with Nexus. Some of the ideas we've been throwing around is maybe the test net, the LISP net, and the production net could be in separate instance IDs. And what that means is that if this 3.3 wants to look up and find out where 6.6 is, it could only get the locators if it's registered in the same instance ID. In other words, any of these EIDs cannot request these guys that are in a different instance ID of 2. So as you see is that other demos running in instance ID 2. We have some public keys registered, and we have some IPv6 EIDs registered, as well as IPv4, okay? So let's just look at 1.1. This is its registration. We just drill in, and we're seeing that there's this system that's actually registering the EID 1.1. And its RLOC set has 2 entries in it, 20037 and 172.1703. So for instance, those would be its RLOCs on each of their interfaces. These containers have Ethernet 0 and Ethernet 1. So what can happen is we could measure the latency. Anybody that wants to encapsulate packets for this EID to either one of these, we could measure the latency and decide what is the better path. And we plan on having the Nexus code, the Tritium code, actually look at paths. If there is some policy that's put in place in Nexus saying 1.1 is a Nexus peer, but these two RLOCs have high RTT, maybe Nexus will use another peer to send transactions to. For instance, we could go back to, oops, sorry about that. Let's get that logged in. Oh, I think it's the other way around. So let's look at like 2.2. Well, 2.2 is going to have, they're all multi-home the same way in the topology. But if this guy, you know, maybe 2.2 is a better Nexus peer to go to because these RLOCs are less congested in the internet. And you know, these RLOCs in real life can be, you know, you may be connected to your LTE interface, and then this might be the IP address that you get from a Wi-Fi interface. Now these addresses will typically be dynamic and they'll be allocated to the systems using existing methods like DHCP. So when your laptop powers up on your Wi-Fi at home or wherever you are at work, it gets an IP address from the access point. That will still continue to happen. But your identity at the network layer will be described by this endpoint ID or EID. Okay, so let's have a look and see what's going on. Let's look at 1.1's. So what I have to do real quick is come out of here. And I'm going to go to 1.1, which is this port number. And I want to it's JDC. I should have known. Here, there's 2. Well, we'll go to 2 this time. So let's just look at 2. What is it doing? By looking at 2 here, what we're showing is this is the map cache. In other words, if any application in this container is sending to any of these EIDs, LISP will say, I need to encapsulate, like if this is 2.2, if I need to encapsulate to 1, here are the 2 RLOCs, as you can see. Let me stretch it a little bit more. Okay, and as you can see, this 2.2 has entries for all 10 EIDs because Nexus has connections to them. When you see these light green, it means a packet was sent in the last minute. If you see dark green, it means it's been in the last second. So you see we're 1.1 has been pinging everybody, and he's sending it at a higher rate than the Nexus keep alives that are going. So you see that we sent a lot of packets through to him. In other words, he's pinging, 1.1 is pinging this 2.2 and it's replying back. So you see that what's going on there. Okay. I could pause 1 minute for questions before I go on to multicast. Let me unmute so everybody can talk. Unmute all. Any question?
Shay, hi Dino, it's April.
Hi, April.
Shay asked a question in the Slack. He said the limitation for LISP multicast not working with IPv6, does that apply to addresses on the LISP overlay?
Okay, let me mute and then I'll answer the question. So if so what we did was in this demo, let me go back to this. Let's see, so I can answer the question correctly. So if you look at this middle diagram, it's the same diagram as above, but it's just showing you that these 3 are joined to this group and these 3 are joined to that group. So what we decided to do here to show the robustness of the topology and what our options are for design is that we decided to use the 224.111, which are all the XTRs, for them to be reachable. So these are overlay multicast groups that were joined. But this one is actually realized by joining a group on the underlay. So that means anybody that would send a 224.1, they would only have to encapsulate to the underlay multicast group, and the underlay would deliver it everywhere. Where for these, we wanted to show that that these would map to the individual XTRs. So when we look at the mapping system, we will see that 246 is actually registered with the unicast RLOCs of each one of those. So yes, there's overlay multicast and there's underlay multicast. If we wanted to do this with IPv6, it would be very easy because these groups could be joined with IPv6 multicast addresses. And we could do that for a future demo as well. You know, it doesn't matter. The question is, how is those multicast packets on the overlay realized in the underlay? And if the underlay supports IPv6, either unicast or multicast, we use it. If it's only IPv4, unicast, or multicast, we can use any 4 of those methods on the underlay to get access to it. And the thing is even though you may have pockets of support for IPv6 and IPv4 multicast and IPv6 multicast, each XTR will know if there's reachability with multicast or unicast for that address family and type. And if it doesn't, because it's probing, it knows if it's reachable or non-reachable. If it's unreachable, it doesn't use it. It doesn't encapsulate packets to it. So what it does is it encapsulates across all the best RLOCs. You can prioritize the RLOCs, and you can load split traffic across all of them. And then we can put policies in that if we're load splitting across more than one RLOC, and the RTT is maybe 20% higher on one versus the other, we can say, let's just use one and not the other. And if there's a change in one, we can move. So all this telemetry data that's going to happen underneath is going to be very useful to have a really optimized network delivery mechanism for Nexus. Okay, so I hope that answered the question. But we can run IPv6 multicast on the overlay across an IPv4 internet. I'll unmute and see if that was that helpful. Did I answer the question?
Yeah, I think that's good.
Okay. Okay, so now let's go back to the map server.
Just one thing, you don't need to unmute us all. We can unmute ourselves whenever we need to. It's just you just have a single mute button just in case, but we can unmute ourselves at any time.
Okay. Should I say unmute all then, you think?
No, you shouldn't. Just leave it and people
Leave it
can
the way it is.
unmute themselves.
Oh, and then you can unmute individually. Okay, that's good to know. Yep. Thanks, Paul. I assume that was Paul.
It was.
Okay. It's the accent, right? Okay. Let's go ahead and look at the map server. Let me move this out of the way a little bit. Timed out quickly. Okay, so now what we're going to do is let's look at the mapping system and focus on these 3 entries, okay? So remember we said all XTRs are joined to 224.111. I'm going to zoom in here and look at that. Now, you notice all 10 of them are sending map registers saying that they are joined to this 224.111, and they're all reporting this 239.111. This is a multicast group as well, but they're saying that is the RLOC, the underlays multicast group for all of them. So all that's being used by any encapsulator is just one outgoing RLOC, and then the underlay will deliver it, okay? If we go now to 246, remember we said just XTRs 2, 4, and 6 are joined. If we zoom into here, we see that each one of them has registered for the 246 group, but they've each registered their own unicast RLOCs. And what happens is they're merged. And now when somebody wants to encapsulate, they head and replicate to each one. So if the underlay doesn't support multicast, we can give a multicast delivery service model to Nexus by saying, if you want to send to multicast groups and you want nodes to join and you want to send and receive, the LISP overlay will give you that group participation regardless of the underlay supporting multicast or not. And we could also add combinations. One of these RLOCs could be a 239 address. In other words, one of the RLOCs could be multicast, and wherever people are joined, RLOCs are joined for that multicast underlay, they'll get it with a single copy. So there's a lot of flexibility by doing this joining and keeping track of receivers in the mapping system. Just to be complete, let's go to 3, 5, and 7. 3, 5, and 7 is another group. And you see that there are different addresses here that represent XTRs 3, 5, and 7. So let's just do a quick ping for multicast and see what happens. Let's see, hit something handy here for me. Let's do I have this script called ping multicast. And I think it should just work like that. No such file or directory. Oh, because I am not in a container. That was the right thing to do. Okay, I'm going to stop this. And oh, wait, that's right. This happened at the demo as well. So I can get, because it's running in attach mode. This is coming in through a bash thing. So now I should be able to do this. Okay, so let's watch for a while, and then so the first thing that happened was this guy is pinging group 246, and what we should expect back is only ping replies from 2, 4, and 6. So we're receiving them. That's one. Let's see, I forgot how many did I send. I didn't show it. I think I sent 3, and you see the 3 responses coming back. Okay, let's go down a little bit, not more. After we finished 246, we tried pinging 357, and what you see is 357 is responding once, responding again, and responding again. And now this is the cool one. The cool one is 224.111, which means a single message is being sent by ping to 224.111. LISP in this system is actually then encapsulated to 239.111. So one message is being sent out here, and then you should see 9 replies get returned. Did we fill it all up with 9 replies? 10, 9, 8, 7, 6. I don't see 5. Oh, there's 5, 4, 3, and 2, and he's 1 himself. Okay? So that was the first demo. That's just showing you the power of multicast. If you want to know how we're going to use multicast, I mean, we have lots of ideas on how to use it with Nexus. Colin has a lot of great ideas using at the L1, L2, L3 layer, or with minor pools within a layer. I don't know if Colin's on. Is Colin on? If he is, maybe he can mention.
No, he's flying at the moment.
Oh, okay, okay. So that's the demo. I know it ended a little bit short, but we can now go ahead and shoot your questions if you want. Let's see if I can find the chat. Okay, I guess I'll stop sharing. Okay. Let's see.
What are some cases for using multicast?
What are some
with Nexus?
With Nexus?
Yeah.
So some things I've been thinking about is if you want your transactions possibly to get to closer peers, to get them, quote, to miners or quicker, that you can then have these geographical groups. So for instance, Anastasia, if you send a transaction and you're in Tempe and you send it to group 224.1.1, we could call these locally scoped groups, and everybody can join 224.1.1.1, but the scope of the group could be in different cities, and then you could go ahead and multicast your transaction to miners that are geographically close to you. So we can reduce the negative effects of speed of light and the number of hops through routers and queuing delay and opportunity for packet loss. We can reduce all this stuff because you're sending things closely to it. And then those guys could then do hashing or prime clustering or whatever the case may be. That would be one example. Another example is maybe all the L1 mining groups that are running in Tritium would all be part of one or more groups. And based on reputation, as they increase their reputation and their, with Coinage and trust and all that kind of stuff, they could graduate to different sorts of groups, and we can then they can receive transactions sooner and get and are able to process them and put them in blocks and put them on the blockchain faster. So
and
that's
that could work.
Go
That
ahead.
could work for like seed nodes as well. So you can basically ping all of the seed nodes if something needs to be checked at that level, right?
Yes. Yeah, you could. Yeah.
So Paul also has a question. He says, you mentioned telemetry data being captured and used to make decisions on routing. Where is that telemetry data processed and decisions made? Is that in the map server or at the XTR level?
It's at the XTR level because you want to look at each XTR's map cache because it's from their perspective in the network how they can reach everybody. So what I've done is I wrote an application called Locator, and that's something I could show at some point. And what it does is it will pull via a RESTful interface. It will pull the ITR's map cache. It will go through all the RLOCs and all the RTT estimates that LISP is computing and the hop counts of the RLOCs are made available in JSON and put in a directory. And that directory, Tritium is going to read to do whatever it wants. Now, I took it a step further. Once you're able to get the hop counts in RTTs, I actually, in this program, run trace routes to each of the RLOCs. So we can actually find the underlay hops, the actual router hops along the way. And then we could also measure the RTT times at each hop by just doing a difference, doing some simple math. And so that's all available too. So, I mean, Brian Smith and I just had a conversation earlier today. We're thinking that on the globe, we can show, like when you show on the new wallet, we show these beautiful arcs that are going to all the peers from a wallet's perspective. Well, when we show them going to EIDs, they would be the same arcs. But maybe if you want to drill in and say, what are all the paths to that particular EID, now we can show multiple arcs, one for each RLOC, and we can show the hop count and the latency. And so these are things that give more perspective to the user, more information. Now, in terms of policy, and when we switch and do all that, that's what we're going to experiment with that over time and decide how proactive we should be. Is we have the information now, so let's first provide the information for monitoring. And if people think they're getting bad performance, they could spot why. And then, you know, we can decide, should they be proactive and should we put policies in to change things? Because the problem with taking monitored telemetry data and acting on it is if you act too quickly, you get these oscillation events. And so do you damp the changes? These are all things that experimentation is going to be useful. Number of transactions coming from different parts of the world will have to be looked at. Everything, it's all deployment stuff that we'll have to look at. And this community is going to help us with that. They're going to provide data from their perspective. It's going to be tons of data. So everybody from their region of the world is going to provide data saying, by looking at this data on the globe or whatever, or I'm finding these typical patterns through BT or Orange or NTT or Verizon and AT&T, or from my home access provider, or maybe my access point isn't configured well at my house or something like that. These are all we're going to be able to find and fix problems really quickly. And we're just going to make it a better network and a better experience for the stakers and the miners and everybody who's involved.
So that telemetry data you said is all going to be pulled via an API. So it's not actually going to be part of the Nexus code itself. It's going to have to. It's a third-party pull of data, right?
Yeah, it can be part of the packaging of the whole. When we package Nexus all together, we can include that and open source it, of course.
Yeah, I'm just thinking this could be a nice little extra module that goes into the UI to have a LISP telemetry monitoring utility, whatever you want to call it, as an extra tab, an extra.
Absolutely, yeah, that certainly can. We can certainly do that. Yeah.
When to log then, Brian. Cool, thanks.
No worries. Any other questions? Any basic stuff? Let me see, I'm going through that. LISP node and Nexus node refer to the same thing. Yes, absolutely. Basically, what we're saying is what we said at the conference is that this is a node that runs the Nexus daemon and or the wallet, and then the lispers.net code, which is my code that runs Lisp, runs at the network layer, and these things are one and the same thing. And of course,
I got a question which I think I know the answer to, but just more for everyone else's benefit is in terms of deployment. At the moment, you've been using Docker as a mechanism for deploying the Nexus daemon and Lisp together. Is that? Can you just explain what that is to everyone else? And is that the decision we made that is how we're going to deploy this?
Yeah, so the reason we're using Docker containers to package the Tritium software is so we can run lispers.net and the Nexus Tritium code in Debian Unix, and we can do it on any platform. Now, with the wallet running, the wallet depends on UI stuff on each platform. So what we were able to do is the wallet will run, of course, on Windows, Linux, and Mac OS. But when it wants to talk to a local daemon and it's running Lisp, it can talk across the Docker container boundary. And we think it's going to be very much easier for people to deploy Lisp and Nexus with a lot less configuration. We want to really make it very plug and play, you know, for all cases. And once we start looking at doing this on a minor platform, we'll look at maybe, you know, like for Blackjack's code, we can package his stuff and this Docker container package as well. So now a miner can do the same thing, right? So
does that mean that
go ahead,
we're
Paul.
not going to be able to compile? Does that mean we're not going to be able to compile our own code then? That we have to use the Docker containers, the images?
Oh no, you can compile your own code if you choose to, but the build procedures will be doing Docker build and rather than typing make in. That's the only difference. And I've documented quite a bit in the Tritium repository. You only need to type in a couple commands, and all this stuff is built for you. So what you should be able to do if you're let's say you're a first-time user and you have Windows, what do you have to do? If you already have Docker installed on Windows, wonderful. If not, we've told you how to install Docker really easily. And then what you do is you do a Docker build, and then you load the DMG or the equivalent for Windows, and then you just bring up the wallet application, and then everything is running. And you will have persistency across that Docker image. So if you stop the Docker container, which you don't even have to worry about or know about, or stop and start it, all the data structures and all the files, you know, all the blockchain data is all, you know, persisted and maintained. If you remove it and come back up, we are going to make EIDs persistent because we want EIDs and key pairs and username, password, pins all to be persistent because they're associated with wallets with funds in them.
What about the blockchain data itself? Is that does that exist inside the Docker container, or did we make a decision that it needs to sit outside it in order to also be persistent?
Funny you say that, because we've tried it both ways and we found the performance slower when it's not in the container. So as long as the container stays up, the data stays persistent. When the container gets shut down, we could copy it to the host file system. And when we come back up, I have it working right now where when it comes back up, it checks to see if the data directory is in the container. If not, it copies it from a specific location in the host OS. This is something we could show later when we have done. So what I'm doing is I'm testing the Docker packaging with Tritium Trust, the 253 stuff, as well as Tritium in two separate efforts. And in the Tritium effort, I'm assuming everything is EIDs, but in the Tritium Trust, I'm trying to run it in this hybrid mode where Nexus is running to just regular IP address peers, but if it's also configured to have a 240 EID address, it can use the 240 EID address and still talk to the peers. In LISP, we have RFCs that say how to interwork. And interwork means a LISP site that has an EID can talk to a non-LISP site or just a legacy site. So for instance, a particular container could ping 8.8.8.8, which is Google's DNS server. Well, Google's DNS server doesn't run LISP, but if we source the ping from an EID, we can make it interwork from the standards. So that's what I've been playing with. You know, Abib has been helping me with it as well. He's been doing some preliminary, you know, assistance, and I'm going to try to get him on the bandwagon to test more too. But this is all in an effort to make sure that the LISP infrastructure and the mapping system work well for Tridion, right?
Yeah, sure. Sounds like it would be good to see if we can figure out why the performance is impacted if the blockchain data is sat outside the Docker container. So if you could resolve that, then we don't need to worry about copying it out in order to make it persistent. But anyway, well, getting outside of this call really.
Yeah, so I think the copy out thing is just a temporary means just so we can keep testing. The problem we're having is Docker is slowed down, and it's a known bug. So we may have to try some newer versions of Docker to see if they've fixed this problem. Because from the container's point of view, it's remotely mounted. And I only have one container accessing the host volume and not multiple ones. So it's not a performance problem. And the container is not I/O bound or CPU bound, so it's just latency and Docker doing the copy. So I'm not sure exactly what it is, but yeah, you're right. I think that's something we need to investigate. If anybody wants to look into it, you know, we can definitely use the assistance. Okay, let's see. T says to everyone, will this speed up local transactions? Can a local network process and confirm transaction within itself? Yeah, it certainly can. I think you probably want other nodes to confirm transactions because that provides better consensus, right? But locally, we don't see a problem because we see the Qt wallet can run where the daemon is not even on the box. It's somewhere remotely. So we're using the same RPC mechanisms as well. I guess when you in that bifurcated mode, the local transactions are going to take longer because you have to go over the network versus starting it out locally. But you know, we have this flexibility in deployment to do either one of these things, and we're going to experiment to see what's best in terms of scale and security, performance, all that.
I had another pretty basic question if nobody else has anything.
Go for it, Paul.
How is the EID initially generated, and is there any way that it can be spoofed?
So what we're doing now for these the container packaging is that we want to start off using 240/8, and that gives us the low order 24 bits to randomize. So we're hoping that the randomization will be sufficient enough. We're going to get to a point where there might be duplicate address that are created, and we'll do the detection and then have the node start up. But when you start up Lisp in the container, it will go ahead and allocate address, register to the mapping system, and then as seed nodes learn about these 240 addresses attaching to them, those 240 addresses will be spread around to the edge nodes, and they can connect to them directly. So that's how EIDs will be assigned and randomized and distributed. Okay. Your next question was, what was the last part of the question?
Yeah, can the EIDs be spoofed? I mean, if you have access to the source code, I guess if it's random, then maybe not. I'm thinking, is there a way that you could know that this is somebody else's EID and I'd like to, clone it, spoof it, make myself that EID?
Right. So yeah, the first part is there's no EID hard coded in the code, so you don't know what it is. Can you spoof it? Well, if we put some admission control into the network, we could actually, if somebody tries to spoof, and we think that a particular set of randomized addresses are supposed to be geographically somewhere, we could reject it. But we want to be open and decentralized and allow anybody to come in. So if somebody tries to register and we see that they're a different set of RLOCs, we're going to have to put some policy in and some code to say, why is this EID changing RLOCs quickly? Is it a legitimate EID going down a high-speed train and the RLOCs are legitimately changing, or is it somebody trying to spoof? So this is something we're going to have to work out. If you have any ideas, Paul, please send them.
Yeah, when I get a chance to look at the code in detail, I will, but I still haven't got there. Okay, so I suppose that there needs to be anti-DOS, protection in there as well, right?
Absolutely. So for starters, what we'll do is we won't allow duplicate addresses, because we will assume that, at least for the first initial releases, that mobility is not going to happen at high speed. So what we'll do is we'll put some hysteresis in there to allow RLOCs to change, maybe on a 15-minute basis or something like that. And why 15 minutes? Well, maybe you are done at work, you close your laptop, you go home and you fire up your laptop, so your RLOCs changed from work to home, but there was traveling time, so it looks like it's a slow mobility event versus a spoof. If we see it happening more often than that, then we know that maybe somebody is trying to, somebody is trying to spoof an address. And we might have to randomize it because we don't want the hacker to guess what the travel time is home, right, or something like that. So, yeah, all the security stuff is very interesting to learn and play with. So.
Hey, Dino, I have a question. Just about the latitude and longitude for each of these RLOCs. I was just wondering how we're going to resolve that so we can actually put it on the globe correctly based on its location.
So there's two ways we could do this, Brian. We can have another RLOC that actually has the geo coordinates, and that LISP natively could support that. So you could take those geo coordinates from an RLOC record that you'll have access through the RESTful API, and then you know how to plot it. But the other way you can do it is just take the RLOC, and just like you're doing now with addresses, you're using a website to find out where it is. This would be no different. You would just find out. You would do like there's many websites that tell you based on the IP address. Since the IP address of an RLOC is tied to the attachment point of the network, then you know if it's attached to Comcast or AT&T DSL or a Wi-Fi in Tempe, Arizona, or something like that. So I don't think you have to do any extra work to be able to plot where they are.
Okay, so we'll end up just having to register with like the MaxMin database people for different locations. That makes sense.
Yeah, whatever you're doing now, you would, when you pull to get the RLOCs, you just run that to how you're doing it now to plot it on the globe. So it would be no different. You're just applying addresses that you don't even care about. If they're peer addresses, if they're RLOC addresses to you, you're just passing those 32-bit numbers to somebody who's telling you where they are. So
cool. Thank you.
I have another basic question. How exactly does LISP secure all of the identity information? So you have this EID that's connected to you and all of your data, and it's sent over through these data packages. How does it secure that information that nobody can get to it or find out all of that personal stuff?
Yeah, really good question. So if I'm going to send to an EID and the RLOCs come back, and there are two RLOCs that, say the EID is Brian, right, and the two RLOCs are his attachments to the network. What we do for each of the RLOCs is, in LISP, is we do an ECDH, elliptic curve Diffie-Hellman key exchange. And what happens is before we encapsulate to the RLOCs, we encrypt it, and then encapsulate it. And then on Brian's side, he will then decapsulate it and then decrypt it, which means all the flows that are encapsulated are all encrypted. So you can't see any of the payload. So what's in the payload? The payload is the actual inner header and data payload that Nexus built. So the EIDs are obfuscated. The data inside the packet, if they're inventory or get blocks or whatever the messaging are, nobody can see what's going on. So a man in the middle can't tap in and find out this Nexus address is sending 1,000 Nexus to another address. It's completely private. Any other questions? Basic ones, complicated ones? Any questions? Okay. Okay, so probably in the next few weeks, we'll look at this container set 2 and have another one like this. Please give us feedback if this was the right amount of time, the right depth level. Oh, actually, we won't do container 2. We'll do, well, if you want to do list, yeah, we'll go in order, I guess. We'll do list decent. The last meetup was talking about what list decent is. Here we can show you what it is. So. And then, you know, as we get further development on Tritium, we could show bits and pieces of our progress so people understand where we are and how much more we have to do.
Awesome. Thank you, Dino. That was great.
Okay.